Hello everybody, so we are back again. Um, what we are discussing just a little before that, we have now caused the breakdown of the gas and formed plasma. Now what we want? We want to know what is the composition of the plasma. Here I have just shown you one example of nitrogen oxygen plasma, and it is this y-axis is plotted in log scale, but this x-axis is plotted in linear scale. So you can see the kind of number density that you are getting over here, and this is at 1 atmospheric pressure, and this T and TH, there is electron temperature and heavy species temperature, they are both considered as equal. So this is considered as a thermal plasma, and we are considering a N2O2 ratio as 8:20, and you see that first initially there is only N2 because the temperature is so low. So all of them are this N2 molecule, and then the oxygens are also in the state of oxygen molecules. So N2 is to O2 ratio that is there, which is maintained as 80:20. And then what you are getting that as you are increasing the temperature, then different species are evolving, like this oxygen, nitrogen atoms, then O2 plus, O2 minus. Then you see that as you are increasing the temperature, it is as it is reaching near say 10,000 degree Kelvin. So you see that the ionization of that oxygens and nitrogen atoms are happening, and what you are seeing here is that you are getting oxygen plus, and you see here this is the oxygen plus and this is N plus. So these curves are coming over here. So here the ionization started over here, and as you reach near say 10,000, so here what you are seeing that N plus plus and O plus plus also have started forming there, and near 20,000 you see here that in triple plus and double plus they are also started forming over here. Although you see that this is plotted in log scale, so you can see the order. See, it is 10 to the power 10 order and it is a 20 to the power 24 order. So 14 orders of magnitude difference is there, but because of the log scale only you are able to project that in this composition graph. So what you are seeing over here, the scenario as you increase the temperature, how the density of different species varies. Now how we got that thing? We started with the ionization equation. So this is the generic equation, as we have told a number of times in our regular classes and in the previous review also, that this is a generic equation, and you can put values of R starting from 0, and you will get different ionized states. So once you know the composition of the plasma, then you can find the thermodynamic properties like density. This is the physical density, and you are summing up over all the species and their masses, and you are getting the density. So this N is per meter cube, so you are getting the mass kg per meter cube. So this is the physical density. Then what you are doing, you are getting the specific energy. So you are adding up on all the species and their energy, and then energy, how that has been calculated, it is calculated from the partition function. So you see that this partition function basically playing a very important role in calculating the composition as well as determining the specific energy of the species. So now specific enthalpy is calculated from them like this, and then specific heat using the standard thermodynamic relationships we are getting. So once you know the composition, you can get the thermodynamic properties using the standard formalism as described in this slide. So then partition function, as I told you, it is a very important thing to understand. So the hierarchy goes like this. Total partition function is product of translational and internal partition function, and internal partition function is a product of this rotational, vibrational, electronic and nuclear partition functions. But if you are considering a say monoatomic molecule, then you are having no rotational or vibrational partition functions. We are having the electronic one mostly. And you can nuclear contribution can be neglected in most of the calculations. So for internal partition functions, as I told you that for molecule it will be rotational into vibrational partition function, and translational partition functions expression goes like that. This you have this you have come across in many of your statistical mechanics classes. So this is not any new to you. Now this electronic and rotational and vibrational partition functions, they have to be calculated properly for specific systems. So here, this apart from this atomic, you are getting ionic and double ionic contribution for the internal partition function, and that has to be calculated. And for electronics, you are seeing that the internal partition function is just a factor of 2. So you are then coming for the explicit form of this rotational partition function, vibrational partition function, and electronic partition functions. Here they are the expressions, and you know that this internal rotational and vibrational internal partition functions can be expressed in closed form using some rotational temperature and vibrational temperature as described over here. So we use that and we calculate the partition function, and then we get the thermodynamic properties as we have described. Now for the transport properties, we start with some interaction potential between the interacting particles, then we get the deflection angle, then gas kinetic cross section, then collision cross section, then collision integral. So these are the equations that we handle. And for the plasma specifically, this charge-charge interaction is one of the major interaction mechanism. So for that, we have calculated the collision integrals using a closed form expression like this one for this charge-charge collision integrals. Now here I have just shown one example of different types of interaction that may happen. Taking an example of N2O2 plasma, you see that different types of interaction that you have considered here is neutral-neutral, ion-neutral, ion-neutral resonant and non-resonant, then charge-charge and electron-neutral configuration. So we have used different color codes, and you see that if you consider different species inside the plasma, the kind of interaction that may happen over there. And you see that there are 17 species that have been considered for this N2O2 model, and all these 17 will interact with all the 17. So you can understand that 17 into 17 total number of interaction will be there. But if you consider the interaction AB is same as interaction BA, then what happens actually, you can eliminate half of them and you are left with the remaining. Still then also the total number of interactions that you need to handle is quite huge. You can see from here, and this color codes presents the different type of interactions that happen, and you can see that most of the part is covered with this yellow color, and this yellow corresponds to charge interaction. It is natural because what we are doing, we are handling plasma system where the most of the interactions we expect to be charge, but the other interactions like electron neutral, then ion neutral, and then neutral interactions are not negligible. You can see they also contribute significantly, but the most prominent contribution comes from these yellow regions, that is the charge interaction. So different transport properties we calculate from the collision integrals. This these parameters are expressed in terms of these collision integrals. So there are certain expressions which are already available in literature, by wherefrom you can get the explicit form of these elements in terms of these collision integrals. So once you know the collision integrals, you can calculate these elements and you can calculate the transport properties like thermal conductivity of electrons, heavy particles, electrical conductivity, viscosity, all these things. So there is another thing which is diffusion coefficient in plasma because of the huge gradient that exists in plasma, both in temperature and number density. Diffusion plays a very important role, and different diffusion coefficients that we consider here: the binary diffusion coefficients, general ambipolar diffusion coefficients, general diffusion coefficients, thermal diffusion coefficients for electrons, ambipolar diffusion coefficient, then thermal diffusion coefficient for heavy species. So all these diffusion coefficients can be calculated precisely from the collision integrals, as we are seeing here. So they are just algebraic manipulation that you need to do, and you will be able to get all the diffusion coefficients as well. So what finally we are getting? We are getting all the transport coefficients and the thermodynamic properties. So once we know these things, so it is necessary to validate what you are getting from there. As you see that whatever we have calculated using the formalism, they are matching very well with those which are reported. There are little bit deviation from the reported values. Sometimes they are matching with most of them, sometimes some of the calculations are varying. So this kind of variation happens because the collision integrals, when you are calculating, there are certain uncertainties in finding the exact values. So because of the different set of collision integrals, this slight variation is happening. But you know that this slight variation in the transport properties eventually doesn't lead to very wide variation in the final properties of the plasma. Little bit variation in the transport properties doesn't affect in a huge way the ultimate behavior of the plasma. So you get quite reliable behavior of the plasma using these transport properties, and they can be verified experimentally. So over the years, such validation of the simulation results with experience have been done, and people are now very much confident about the simulation results to design their device and to understand the process that may happen inside a reactor with a specific design. So these are the role of the transport properties. Then there is ambipolar diffusion coefficient in plasma. I have shown in a bit emphasized manner, because this is a very very important and very peculiar diffusion inside plasma, because this ambipolar diffusion is called ambipolar because both the positive and negative species, they are drifted in the same way. So ambipolar diffusion coefficient is defined like this: mu I d plus mu di by mu I plus mu, and the diffusion expression, this diffusion equation, that goes like this, and this d is the ambipolar diffusion coefficient. So you are seeing here that mobility of electrons, mobility of ions, diffusion coefficient of electrons, diffusion coefficient of ions, both of them are appearing here. So they are involving both the polarities of the species that is present there. Now the way a plasma diffuses with time, that has been shown in this graph. You see that this is in microsecond. So initially the population was like this, then that gradually dies down when you solve this diffusion coefficient, diffusion equation. Now what are the features of this diffusion coefficient, ambipolar diffusion coefficient? What is seeing here, that this can be expressed as di into 1 plus T by Ti. This is because this mobility of the electrons is very high compared to the mobility of the ions. So if you use that property, then this ambipolar diffusion coefficient can be expressed like this. So what you are seeing here, that diffusion is controlled by heavier species for thermal plasma when T of the order of Ti, and you are seeing that this is in general, actually this diffusion is controlled by the heavier species only, but when you are considering thermal plasma, T of the order of Ti, and you are seeing that ambipolar diffusion coefficient is just twice the Di value. So, this is one very important consequence, that the diffusion is getting ultimately controlled by the heavier species. So, the highly mobile electron is not able to control the ambipolar diffusion. It is the heavier species which are having smaller mobility, lower mobility. They are basically controlling the diffusion process. Now, uh, electric field. Electric field, when you are considering this ambipolar electric field, so that you are seeing here that it is decided by grad n E by N E and get kt E by E. So, everything here you are getting in terms of the electron properties. So, electric field governed by the ambipolar diffusion process is controlled by the lighter species. So, there are two things. One is your diffusion itself, that is controlled by the heavier species, but the electric field that is generated in this process is governed by the lighter species, that is electrons. So, these are the take home messages for as far as the ambipolar diffusion is concerned. Then these are the different diffusion coefficients, as I have already told you. Now comes the non-equilibrium system equations in terms of fluid model. This we have discussed many times, and here the body force terms J or B theta, and this is JZ B theta. So, these are the components, body force components, which are arising only because of the J cross B force. Then this in the energy equation, this is the Joule-Rating term, this is the K dot Gadry term for diffusion, and this is the this collisional exchange term, and this UR, this is basically the radiational loss term. So, these are the specific or distinct ways by which the plasma dynamics differ from ordinary gas dynamics. So, this is a fluid model which gives very reliable results when you go for system design. Now, when you go for solving, so one is your fluid dynamic code, where you need to solve this conservation equations, but the coefficients here, this viscosity, it is electrical conductivity, this is your thermal conductivity, all these are the transport properties which has to be given by specific property code using the formalism that I have already discussed. So, the fluid dynamic code and the property code works in unison. So, property code provides the transport and thermodynamic properties, then fluid dynamic code calculates the field values like your velocity, temperature, distribution. They feed that to the property code, then they get the thermodynamic properties in return, and then they feed that back. So, this goes on and on in loop, and finally what you get a solution which is converged. So, this one this one is the distribution of this electron and heavy species temperature, as you are seeing over here. I think pointer option, I go here, arrow options visible. So, if I go click here, you see the simulation that you have seen over there. So, with time the iteration, this image is evolving. So, you are getting that the distribution, lower half is the heavy species temperature and the upper half is the electron temperature distribution. So, you see that iteration after iteration, it has finally reached to a state where the simulation is still progressing. You see here the bar is increasing, okay, the iteration is moving, but what you are seeing, it is a still picture kind of thing. So, it is no more moving. So, if you start from the beginning, you see here that when you started, it was evolving, right. So, with iteration, the field values, they have the temperature that is evolving. Lower half is the heavy species temperature and upper half is the electron temperature. This is a non-equilibrium simulation. So, you are seeing here that the temperature distribution inside the device is nearly similar in the core region, but when you are going to the periphery, the electron temperature is much higher compared to the heavy species temperature over here. Similarly, here you see the pressure evolution. So, this green one or rather the blue one is basically the atmospheric pressure. So this is cathode, this is anode. As the simulation is evolving, you see that finally the pressure is getting released at the exit. Here it is almost matching with the atmospheric pressure. As the simulation will proceed, you will see that this is a blue color you will be seeing over here. So that means now it is getting released at the atmospheric pressure through the nozzle region. And the interesting thing is that the pressure, high pressure region is extending quite deep inside the plasma device. So this is a 2D simulation. So you are seeing only one part of this, so that you have explained here. So the interesting thing is that the way the simulation proceeds, that is reliably giving you the distribution of temperature within the plasma device, which will help you to understand what is the kind of temperature that will be evolving inside the device, and what kind of process you can do using that kind of plasma system. So that is up to the simulation process. Then this is the distribution of electrons, how they vary. This is very interesting because you see here, this is the bluish region, this is the yellowish region, so density is low. Here, why the density is low? Because this is a very high temperature region. Here the second ionization, so these are basically second ionization starts over here, and because of the very high temperature, the density is less. As you go little periphery region, the density is increasing over here, and then again decreasing because of the lower temperature. So these are the O plus second ion density. As I told you, because of very high temperature over here, the density of O plus plus only seen over here maximum, then it is decreasing. Now coming to the plasma sources, we explained how it operates. So there is a cathode, there is an anode, and gas is flowing between these two. All of them are intensely water cooled so that they can bear the kind of temperature. Say in the core the temperature is more than 10,000 degree Kelvin. So the region of the medium that is in touch with this coolant. So here there is a very cold boundary layer. So that is basically saving the electrodes. So that is the fundamental thing. And the cathode, usually we are using tungsten cathodes in many of the cases, which is thermionic emission. So you need this cathode to be heated a bit. So here raising the temperature is actually a desired thing, so that you can get copious emission of electrons. This thoriated tungsten, which has lower emission coefficient, lower work function, so that it can emit electrons at lower temperatures. So these thermionic cathodes are used over here. Initially the breakdown is happening using a high frequency field like AC breakdown that we have just discussed in our regular classes. So that is causing the initial breakdown, then bias is applied, and that is making the arc to form over here. This arc is hitting the gas that is passing through and forming the plasma jet. So this is typically the mechanism by which the plasma is formed. Now if we want to increase the voltage, then what we need to do, we need to insert the segments, and we need to connect this arc from here to here. So when we do that thing, then because of the increase in length of the arc, the total voltage drop increases, and we get a higher power inside the device, because these devices are usually operated with constant current power supplies. So constant current into the voltage that you are able to develop over here, that gives you the total power that the device is consuming, and part of that will be included in the plasma jet that is coming out. Why I am saying part of that? Because as you increase the number of segments, all the segments are intensely water cooled, so they are carrying away the heat that is dumped inside the plasma. A significant amount of that is getting carried away by the cooling water that is flowing through these segments. So even though you are increasing the voltage by increasing the number of segments, your total power V into I is increasing, but a significant part of that is taken away by the coolant that is flowing through this segment to maintain the structural integrity. So that is how the efficiency decreases when you increase the number of segments, whereas the efficiency becomes maximum when you are using lesser number of less number of your segments in this zone. So finally we have shown that how the arc attaches at the anode. So this is the cathode part and this is the anode. This arc is forming like this. So this luminous zone basically the path of the current, and because the current is extending into the plasma jet, then returning back and entering into the anode, so the point where they are entering, they are highly constricted. So that is why the current density is very high and J square by sigma is the heating, that is very high. So that is making them to be luminous in a very significant manner. So that's why what you are seeing here is the highest luminous zone. And in this zone, the current is basically distributed over a wider zone. So current density decreases, so the luminosity also decreases, because heating is less, current density is J and heating goes as J square by sigma. So when current density decreases, heating also decreases, and we see the luminosity comes down. So there are various electrode materials that are suitable for these plasma devices. We have discussed that. So there are thermionic cathodes, thermo-chemical cathodes. Thermo-chemical cathodes can work in the oxidizing environment, but thermionic cathodes like tungsten cannot work there because their melting point comes down. You see that tungsten is having melting point of 3422 degree Kelvin centigrade, and here you see that tungsten oxide is having only 1473 degrees centigrade. So drastic reduction, that is why tungsten cannot work in the oxidizing environment. Whereas these thermo-chemical cathodes, for thermo-chemical cathodes, when they get oxidized, you see that the melting point increases. So it is around by 500 degrees centigrade. So that is the very key feature of the thermo-chemical cathodes like zirconium and hafnium. So because of low melting point, sometimes these cathodes actually emit in the liquid state. At least a thin film exists on the top of the cathode while they emit. This figure is showing that this cathode was emitting in the molten state, but still when this hafnium, as I told you that the metallic elements, they have very low ionization potential. The hafnium, when they comes out into the plasma because of evaporation of this liquid zone, they immediately becomes hafnium plus, and because the cathode state is a negative potential, so they attract it back to the cathode. So that's how we can limit the erosion of the cathodes in case of thermochemical scenario. So that is how you can use the hafnium cathodes for hours and hours of operation without failing the cathode. So this is you see that after 17 hours it has become a very smooth, and if you see the solid actual image, then you will be seeing that it is a very shining part. This is an actually ACM image. So this is a mechanism by which the ionized hafnium is getting attracted back to the main hafnium part, because this is at negative potential. So this much now in this review. So I think I have covered most of the important features that we have covered in the last 3 weeks. We'll come back again after another 3 weeks to review the key features in the same way that we have done today. So thank you very much for attending the class, and I hope that you are enjoying the classes and you will enjoy the coming classes, and will appear again for reviewing the critical concepts after another 3 weeks. Thank you very much.